Yep, looks good.
All right, good, yeah. And then I'll get my little laser pointer up here.
Yep, we can see it.
All right.
And so I think given the time and that we have a pretty good crew, most people are filtering in, a few stragglers will still come in. I'm going to go ahead and get things started. And we're up on YouTube. So hello, everyone online, and welcome back, all the participants here on Zoom. So I'm really happy to have Konrad giving a sort of seminar for us here today. So Konrad did his PhD at UCSB with James Allen, working on, I guess, superconducting quantum circuits, this kind of thing, and then did his postdoc with Rob Sholkoff at Yale, and again working on superconducting circuits, circuit QED, these sorts of topics. And so today, he's well known working with these sorts of systems, but also I think what we're going to hear about more today, electromechanical systems, quantum electro and optomechanical systems. He's received many awards, most recently maybe the Vannevar Bush Faculty Fellowship, and so it's great we're going to get to hear from him. I'd love to hear how you made the switch into doing these optomechanical type things, because I don't think that was your training. But anyways, whenever you're ready, go ahead, Konrad.
Absolutely. Hey, thanks a lot, Ken. Yes, my PhD work, I was working with indium arsenide with superconducting contacts, not only before it was cool, but when it was explicitly uncool to do that. And the fact that it all came back again was sort of an amazing fact that anyone would care about that again. But
well, you made it cool, maybe, Konrad.
I think that is not the case. Actually, I'm quite confident that that's not the case. I didn't, the Mariana zero modes, or whatever the modern name is supposed to be, were not a thing that people were talking about that much in 1999. So yeah, today I'm going to give a lecture. I think the way to think about it is kind of pedagogically structured research seminar. I will try to maybe give a little bit more of just some of the physical structural details, the way I think about the particular problems, but it's predominantly kind of an introduction to an interesting research topic and an activity in our group. What we tell you about is a topic that I like to call quantum electromechanics. In some contexts is called other things. It's essentially the physics of electrical circuits that couple to vibratory or acoustical degrees of freedom, essentially mechanical motion of some sort. And it's possible to bring both the electrical circuit and the mechanically vibrating and oscillatory thing into a regime where it deserves a quantum description, where one should live a little bit outside of the correspondence limit of quantum mechanics. You can see some genuine quantum effects. There's some kind of set of photographs here, images of different kinds of things that we make in study of this type. I think maybe just as a broad motivation, and to answer Caden's question a little bit, I got involved in this topic because I was genuinely curious about what's like the biggest, most tangible thing that I could hope to put into a quantum superposition of two places at once. I don't know that there's an easy to falsify theory that is worth the trouble to falsify that would say you can't do it beyond a certain size. But I think it's just a sort of scientifically and technologically interesting question to ask. What's the biggest, most ordinary looking lump of stuff that you can put into a quantum superposition of two places at once? So to think about that, often represent the state of a harmonic oscillator, in this case, some mechanical thing, as something with two quadrature amplitudes. Maybe think of them loosely as position and momentum. And the quantum mechanical sort of version of a state with a well-defined amplitude and phase is this coherent state, a kind of like well-defined position and momentum classically, then blurred out by some quantum noise, maybe a little more explicitly here, we'll think about it as the so-called Wigner distribution. The ambition then is to make something where you cut that phase space distribution into two pieces, where you really have the simultaneous possibility of having two very well separated points in phase space. And this kind of thing has become, dare I say, routine for superconducting electrical circuits, like making these kind of Schrodinger cat states where you have really well separated regions of probability in phase space, and yet you're still in a single pure quantum state. And these Schrodinger cat states, they a particular harbinger of something which is sort of interpreted as being profoundly quantum, for example, is like having negativity in the Wigner function, meaning this quasi-probability distribution function cannot be interpreted as some kind of probability distribution function. So that was kind of the motivation. There are like a long history of people thinking about how well you can prepare, measure, control the quantum state of mechanically oscillatory things, really for the purpose of the detection of gravitational waves. Like that was the problem that I think forced the community to address the questions about how do we think about the control and measurement of some big blocky thing which is going to vibrate and oscillate. And in particular, that happened early enough that it was the motivation for developing a lot of the modern ways we think about quantum mechanics, about treating things in these open quantum systems descriptions. This kind of simple. Caden, were you asking me a question?
I was going to, yeah. So I was just wondering, in the gravity wave context, was it really these big oscillators, or was it light, or both that they were thinking about?
I mean, for sure, the early days, were driven by Joe Weber's early experiments, right? The Weber bar experiments in the sort of 60s and early 70s, in a way, I don't know, some of the people who I talked to who sort of knew that generation of scientists say that the early claims of Joe Weber to have seen gravitational waves was a little bit part of the motivation for doing some of the early LIGO things. Sort of like, okay, like, no one can reproduce these results. We have to go build a thing that we think can really measure. So for sure, by 1980, there was a very sort of sophisticated theory and experiment world ramping up in gravitational wave interferometers, what would kind of become the LIGO project. But the early questions, like how shall we think about a harmonic oscillator and its control and measurement, when it's sort of a little too simple to imagine that I should just apply von Neumann postulate to the measurement of the thing. Like I don't have a meter that does exactly that. I'm going to try to continuously monitor its position while I imagine that it's continuously being driven by some weak classical force. And that led to notions like standard quantum limit, the notions of a quantum non-demolition measurement, the notions of a back action evading measurement. It's quite hard to establish quantum control and measurement over something which is 1 ton of aluminum. If you give up on the notion of detecting a passing gravitational wave, which will couple to a big thing, not so much to a little like 5 micron object, but that little 5 micron object, you might hope to relatively more simply establish quantum measurement and control over that. You can sort of like demonstrate and study all of these protocols that were thought about in the context of gravitational wave detection. A thing that you might ask what you learn when you do that. Well, a thing that you learn is kind of what's left out of the original idea. The original idea, for sure, is something which is physically motivated, but there may be phenomena in the actual thing that you make that thwart or prevent you from implementing the initial motions of back action evasion, and there you might need to find some kind of strategy to get around those. That was like a relatively recent thing that my group was involved in. We certainly are not going to be sensitive to a passing gravitational wave, but we can identify and work out modifications to certain ideas that are necessary because of sort of some dirty effect that was sort of not treated in the original concept. Okay, I think mechanical systems, when you shrink them down in scale, they play a role in physical sciences, which is a kind of universal transducer, is the way I think about it. If you say, look, I think I'm looking for some physical phenomenon, and I don't have any direct way to turn that physical phenomenon into a modulated electrical or optical signal, one of the things that I can do is go through mechanical motion. I can use whatever physical phenomenon I'm interested in, use it to create some kind of gradient in the thermodynamic energy of a system, and use it to pull, like use it to create a force. And then the resulting deflection, I'm going to read out with light or electricity. That's how the atomic force microscope works. Maybe a little bit more exotically, the notion that you can detect the nanometer-sized nuclear spin density inside of some material. That is a hard quantity to map directly to light or to electricity. But if you make a very sensitive little cantilever, it can exert a little force. The resulting deflection is what you read out with a laser. Another kind of property of sound, I think, in the classical information processing world, is that it is used a great deal in special places to filter, delay, or create timing signals. And the reason that that happens, from a reductionist perspective of a physicist, is because the speed of sound is slow. Because the speed of sound is 100,000 times less than the speed of light in a characteristic material, for a given resonance frequency, if you make an object that resonates electromagnetically, it will be many orders of magnitude larger than the equivalent acoustical resonator. And that fact is used, for example, in all wireless and cell phone technology to do filtering functions, essentially because you can create filters that use the fact that the wavelength of gigahertz frequency sound is about a micron. And that allows you to make very compact filters with many poles, giving you very flat transmission over a very narrow range in frequency, and then a very large cutoff or suppression of modes that you don't want. The equivalent sharp structure in the frequency domain, to achieve that electromagnetically, to have a 10-pole or 100-pole filter, for that matter, electromagnetically at these 100 megahertz frequencies, would be an unbelievably cumbersome object to put into your pocket. And so it's sort of natural to ask, look, this is an interesting fact that plays an important role in classical information processing. Are there ways in which the slowness of sound can be useful or used in processing quantum information?
Konrad, I have a really dumb question.
Please go ahead.
So probably this would fall into the class of things not nice to put in your pocket, but I could imagine that I could just put like an FPGA after I convert the acoustics to electronics, and then I could put in whatever filter I want.
100% correct. And in fact, lots and lots of kind of filtering and signal processing is now done in the digital domain, when in the early days of FM radio, such a thing couldn't be imagined. Nevertheless, the analog front end of that FPGA, the thing that has to turn the analog voltages and currents into digital signals, that has finite bandwidth and dynamic range, and in particular the dynamic range. If you have a nearby transmitter transmitting at an adjacent frequency channel to your cell phone conversation, and it's making 80 dB more power. It's 100,000 times, 1,000,000 times more power than the conversation that you're trying to have. That would saturate that front-end electronics. And so for that reason, this kind of analog filtering is still critical. Not only, so that critical aspect actually happens at a couple of stages. Before I went to grad school, I worked for a cell phone outfit making chipsets. So I know more about this story than is probably appropriate for me to kind of lecture on at this point. But digital is awesome. You can't do everything in the digital domain. You first, like that analog to digital process that's happening inside of your pocket has real physical limitations, and you need filters to manage that.
Perfect, thank you.
All right. So that's sort of a brief introduction, motivation for why I got interested in doing sound in the quantum world, like vibrations, acoustics in the quantum domain. So I think in the world of people who thought about this as well, there was an early and important idea, really a kind of version of the LIGO gravitational wave interferometer for how you try to do quantum control of vibratory motion. Idea is you have some mechanical oscillator. You could measure its position quite accurately by bouncing a laser light field off of it and just measuring the phase acquired upon reflection. It's clearly, that's clearly going to vary as this object moves. It's this nice shiny mirror, for example. And so I can infer the position of this object with optical phase. Maybe what's a little less obvious, though certainly quickly understood, is that I can push with radiation pressure forces. Like the light is going to exert a force on this object, light carrying momentum, a kind of standard undergraduate textbook problem that you get asked. And although that force isn't very big, it tends to be a thing that you can control very well. If you like, a laser has a lot of dynamic range. It can have a very large amplitude with carry a lot of energy, but not a lot of fluctuating entropy. So you can have a very precise kind of force. This whole story gets a lot better. The scales work out in a nicer way if you put the mirror, if you make the reflecting item one element of a two-mirror cavity, a so-called Fabry-Perot cavity. Now, if you think the same photon that's going to tell you about where this mirror is, it gets to bounce up back and forth, say 1,000 times. It acquires 1,000 times bigger phase shift. Likewise, that same photon that imparts a bit of momentum every time it reflects off the mirror, that momentum kick is 1,000 times bigger. And that led to an activity called cavity opto-mechanics. It is, of course, in some sense, people were forced to think about these notions of both the interaction of motion with light stored in a cavity, but also the fact that the light would really exert a force on the cavity mirrors inside the context of the LIGO interferometer. But it became a kind of scientific activity to say, well, I'm going to step away from the difficult task of measuring gravitational waves and just make a small example of this idea in my lab. This is a somewhat out-of-date picture from the Aspenmeyer group. This object is a very high reflectivity mirror, and it's being attached to a suspended strip of material. This is a tightly stretched thin sheet of material forming a bridge here with a mirror sitting on it. And if you were to push on that mirror with little threaded tweezers, that bridge would flex. It is a physical implementation of this idea of a mirror sitting as a mass on a spring. And out of sight of this picture is a curved mirror and the formative Fabry-Perot cavity. So a thing that we did in our group, and we got inspired to do this, we said, look, can we do this same idea, this kind of opto-mechanics concept, but replace the high Q optomechanical, like the optical cavity, with instead an inductor capacitor microwave circuit. The idea is roughly to build an inductor capacitor resonant circuit where the capacitor in the problem is mechanically compliant. The separation between two plates of a parallel plate capacitor can change. If you like, the mass on a spring is one of the plates of a parallel plate capacitor. Once again, now if you bounce a microwave signal off of this resonant circuit, you can infer the deflection of that mechanically compliant capacitor plate from the phase acquired from the reflection of the microwave signal. And you can also exert a force. You can exert a force essentially, well, there will be a force proportional to the square of the voltage across a pair of capacitor plates. You control that voltage in an AC sense by pumping energy into that circuit. One of the motivations for doing that, one of the reasons we wanted to do this was basically to connect mechanics, mechanical motion, to the kind of quantum control and measurement that has become routine and extraordinarily powerful using microwave frequency superconducting circuits, this kind of world of superconducting qubits. In addition, one of the nice aspects of working in the electrical circuit domain is that it's natural to operate an experiment like this inside of the ultra low temperature environment of a dilution refrigerator. If you would like your experiment to have very little thermal noise that is driving it, if it's built from superconducting metals and measured in the microwave domain, that is a technology that's completely compatible and routine to put inside of these just cryogenic systems that reach these temperatures. So that's the, that was the kind of notion that we had that eventually evolved into devices that look like this. This is a picture of superconducting aluminum, that's the light gray stuff, sitting on darker aluminum. And there is a spiral of that aluminum you can see here in a wire. That's just an inductor. Sliding by that inductor is a wire that's connected to a transmission line. That's a way that you can get energy into and out of the inductor. And then this is the parallel plate capacitor. This is a little disc of aluminum sitting above another disc of aluminum underneath. If you zoom in on that little disc and kind of look from the side, you can sort of get a sense that there's a layer of aluminum sitting on a surface, and it's blistered or buckled up above the surface. And there's a little bit of an aluminum wire that pokes underneath. And you don't see that bottom layer of aluminum, but you see the dent that its fabrication has made on the top layer. And that's now this little central lollipop that you can resolve here. Those two.
Is all this fabrication? Is this something lots of people can do now, or are you really at the edge of things?
I would say that a number of people can do this now, and a number of groups that do this. I don't know that it's a routine yet. I think part of it, it has not attracted the level of industrial investment as quantum computing has. So it's maybe one of the reasons it's a little bit of a niche thing, but this process that does this, it is, I think, possible to do, but it was a hard process to work out how to do it well. It was really worked out in Ray Simmons' group by Katrina Chichak. She was the one who spent a long time figuring out how to make aluminum above other plates of aluminum and get what turns out to be a 50 nanometer separation between those plates of aluminum. But separated over something like 15 microns, but there's no contact between the upper and lower plate. It's really an astounding fact. So I'm going to introduce a small parameter at this point in the talk. And the small parameter is going to be the following thing. This upper
So I have a question.
Go ahead.
In that, I'm not sure if it's relevant here, but in the limits which you're talking about, that like a 50 nanometer between two essentially metal, some of these quantum phenomena, like a Casimir effect, wouldn't bother here?
Oh, the Casimir effect is probably why you can make it 50, but you can't make it 25 nanometers. That's what we think. I won't get into the data and evidence of that in this presentation, but we have some good evidence that in fact we can see that some substantial fraction of the restoring force of the motion of this membrane is really from a kind of Casimir pressure.
Quantum or thermal?
This would be in the quantum case. Not only because we're in a dilution refrigerator, the separation between those metal plates is very close.
Yeah.
So there's another question from Yakov.
Yeah, I was wondering why aluminum? Is it called the low density or?
So number one, a superconductor.
Okay.
Number two,
many things are superconductors, right? So why specifically aluminum?
So number two, of the superconductors that are routinely used in fabrication processes, it has a lot of nice properties that in fabrication in particular, its etch chemistry is quite different than other things. So if you ask how it is that you make a structure like this, you put down a layer of aluminum, a layer of stuff that will get etched away, and a layer of aluminum on top of it. It's important that the stuff that gets etched away, the chemistry that does that doesn't also etch aluminum. And that's not true for another superconductor that's popular, which would be niobium. Its etch chemistry is too awkwardly close to silicon. Why not aluminum?
Well, yeah, of course.
Okay. Of the superconductors that get routinely used in electrical circuit processing fabs, like it's definitely the easiest to work with. It's like the number one thing to use. Niobium would be second on the list, and everything else is harder.
Yes, thank you.
What is the Konrad, can you give us some idea of why, of the shapes, like why circular as opposed to square? Is it, and also like I see some structure, like there are holes in the upper membrane. So why have those holes?
Why do we have the speed holes? Sure.
Yeah.
That's a little bit about the process of how it's made. You want the gas phase chemical that's going to get in and etch the sacrificial layer between the two layers of metal to get in, and you want to provide a path for it to do that.
Okay.
Rob Schulkoff, when he saw this, though, he called it the quantum hubcap.
Okay.
And then why round? I think we spent a long time trying to make strips rather than something which was sort of more disc shaped or like at least square. It turns out that there are attractive forces in the fabrication process that try to collapse the membrane. And if you've ever done the thing of like that you do with your kids to demonstrate that you can make a bridge out of paper stiffer by folding up the edges, that's a little bit why it needs to have more of a, like, not a strip, but at least a circle or a square. I think squares would work fine. We liked the fundamental mode of this one was something that was sort of easy to calculate. You could also do it for a square. I think that works just fine.
Okay. And the wire underneath, that's the contact to that capacitor or to the bottom plate of the capacitor?
There's a wire here that is passing underneath this disc. And that's, that wire, the way I think about it is it just spreads out and forms, like the wire is skinny, and then it gets fat, and that forms the other plate of the capacitor.
Oh, I see. I see.
The thing which you might have noticed, because you have good eyes and you pay attention to things, is that there's a third wire here.
Right.
And that one actually is contacting a second electrode that sits underneath. That wire I won't discuss in this talk, but it's there basically to attract the upper plate to the lower plate electrostatically. If we wanted to, we can apply a DC voltage and pull them together.
I see.
And that allows you to control that separation a little bit. And it's, by the way, how it was that we identified physics that looked like Casimir pressure. It looks like Anant has a question as well.
Well, so
Yeah.
Sorry, go ahead.
Oh, I was wondering how you take this image on the right, or whether it's a CAD model or if it's actually an image at an angle
That's
like this.
Scanning electron microscope picture with false color.
Oh, I see.
Not a CAD model. That's real.
Wow, looks amazing.
Colleagues at NIST are amazing. All right, Leo.
Yeah, just quick question. So if I look at your schematic LC loop, there's the blue plate is contacted with a wire. Where's that wire in the blue contacting the blue plate?
Can you tell me? Let's see.
Well, so
direct my laser pointer.
Well, so I'm looking at your LC circuit.
L.
And there's in the upper right. In the upper right. So there's a blue in the red plate. There's a blue in the red plate. Can you just identify, give some identification for us uneducated in the subject, between the schematic and your plate and your, the images.
I see. Good. So there's an awkward thing in schematic land, which is you have to combine electrical and mechanical symbols.
Right.
So what's intended to be shown here is that this is a loop of metal with a capacitive break, a gap,
right,
through an inductor. And when you pass into the red region here, you imagine there's electrical continuity all the way up to this point.
Okay.
Nevertheless, this is supposed to indicate a spring.
Right.
And so if I were to identify, so if I were to kind of walk from the plate, it's on the bottom in the schematic, but it's on the top in the physical world.
Okay.
I would walk from the center of this plate. Okay. I would walk out through this wire. I would run all the way around through the spiral, round, get to this point. And then I would pass under every one of those little loops. There'd be a wire that actually goes under, this wire passes under all of these loops I just formed. You can kind of see it here, there's little bridges.
Right.
And then that goes then underneath the upper plate and forms this point here, this blue region.
Perfect.
And then this little wire here running by, that's kind of this mutually inductive section here. And that couples to a transmission line.
Perfect, thank you.
All right. So I wanted to say something about scales. What did I want to say about scales? Good. So the upper plate here vibrates mechanically at about 9 megahertz. That's the fundamental vibrational mode of a stretched aluminum drum head with this density tension. And then it's coupled to an inductor capacitor resonant circuit that resonates at about 7 gigahertz. Those are obviously very different frequencies. And in addition, there's a small parameter in this problem. If you ask what's the 0-point motion of this vibratory mode, this 9 megahertz mode, it's some particle living in a harmonic potential, how much is it 0-point motion? It's about 4 femtometers, 4 10 to the minus 15 meters. Even though 50 nanometers is a small number compared to everyday length scales, you can see that it's still quite big compared to this 0-point motion. And so we're going to have a kind of small parameter. It's going to tell us in particular that the 0-point motion isn't going to, if I displace the membrane by about that 0-point motion, I wouldn't change the resonance frequency very much because I would only make a very small fractional change in the capacitance. And there's a big mismatch in the frequencies. In particular, we can identify that the 0-point motion tunes the resonance frequency of this LC circuit by about 200 hertz. Do I tell you the line width of this circuit? Its decay rate out to its transmission line is going to be bigger than that. It's going to be hundreds of kilohertz. So you basically get kind of parametric linear coupling in a problem like this by pumping the circuit detuned from its resonance frequency. And then that creates, if you can imagine, if the mechanical oscillator is vibrating for any reason, including just for the fact that it is an object which has a resonance frequency of 9 megahertz and will vibrate just for thermomechanical motion reasons alone, it is going to have some thermal energy. That's going to modulate that strong pump and generate microwave photons, radiation at the circuit's resonance frequency that will leak out. And so in a way, what you create is an effective linear interaction between the low frequency phonons associated with the mechanical motion here that are going to modulate this pump, creating slightly higher frequency photons that then leak out of the circuit. And if you write that in a kind of quantum description of that process, in the regime where the electrical line width of this cavity is small compared to the mechanical oscillator's resonance frequency, then you're in a limit, you're going to be dominated by a kind of process where the pump photons either combine with a mechanical oscillator phonon to make a slightly higher frequency microwave photon that can run away and leave, or you can insert a microwave photon at the circuit's resonance frequency that can split up into a pump photon and a mechanical phonon. And those processes are sort of summarized by an interaction Hamiltonian, where this weak coupling amplitude of only a few hundred hertz gets boosted by the strength of this drive. That gives you the ability to sort of swap phonons and photons. It's a very useful thing. That useful thing, though, it's important to recognize that this interaction Hamiltonian, it's still linear or bilinear in the creation and annihilation operators. It's something which is going to be fully diagonalizable using trivial undergraduate things that we all learned. It's a linear interaction. You can do stuff with that linear interaction. This is not the primary topic of my talk today, but that linear interaction is super useful. And so I don't mean to tell you that it's boring. One of the things that you can do with it is you can create that linear interaction between electricity and motion at the same time that you create exactly the same kind of linear interaction between light and motion. And in a project that I do collaboratively with Cindy Riegel's group, we work on a piece of quantum technology that's designed to link, in a quantum sense, the microwave and optical domains. We create a single vibrating mechanical oscillator that tunes an inductor capacitor resonance circuit in the way that I described, but simultaneously that same vibratory motion alters the resonance frequency of a high-finesse optical cavity. And by pumping both the microwave circuit and the optical cavity below their resonance frequency, you create an effective linear interaction between microwave photons resonant with the circuit and optical photons resonant with the optical cavity. And you can really upconvert, in principle, noiselessly between the microwave and the optical domain. That's not something we've done noiselessly yet, but we do pretty well. And the idea for that is motivated by the notion of creating quantum communication networks. In our vision, the nodes in such a network would be built from emerging superconducting quantum computing technology, and you would create entanglement between those nodes using links of light traveling through optical fiber or free space. That's really the motivation for creating that kind of quantum state preserving linear conversion between the microwave and the optical domain. You could do other things. That linear process, you can do a kind of signal processing using mechanics. Like you can take a pulse of incoming microwaves, here measured as a function of time, where we have a decaying exponential pulse. The microwave pulse turns on suddenly, oscillates rapidly, but has a kind of decaying envelope with time. We can turn on the pump frequency in order to convert that incoming pulse with near unit efficiency into mechanical motion, where it will be stored and live inside of the mechanics until we turn our pump back on. And then it comes out as some microwave pulse with a temporal envelope that we can choose and control. So you have the ability to catch, delay, reshape, and even frequency convert signals using these kind of linear electromechanical techniques. There's a related way of using these to do entanglement and amplification between microwave and mechanics. These are all things that are possible in this world. But there is no sense in which you would get access to something like a single phonon, a single quantum of sound. That's because of the linearity. This is a theorem. Essentially, if I have a system of harmonic oscillators that interact in the linear way, if they start in something like a coherent state or a statistical mixture of coherent states, they evolve under linear equations of motion, and all of the measurements that you end up making are of the linear amplitudes, the kind of position and momentum like variables of those harmonic oscillators. You'll never escape that world of kind of Gaussian noise, of kind of the coherent states. The notion of a single phonon is kind of hidden. So the story that I'd like to tell you is about how you start to access single quanta of sound, phonons, inside of these kind of acoustical or vibratory systems. So that's really the question we wanted to ask. Can you detect a single phonon? Can you say, inside of this harmonic oscillator, which is mechanical in nature, I believe there is one and only one acoustical excitation, one vibration, vibratory excitation, or zero, not on average one. And so to tell you about sort of two pictures, right? When I was learning the harmonic oscillator as an undergraduate, I was taught to think about it this way: a particle in a parabolic potential. You can write down its spatial wave functions, and oh God, those are some kind of ugly polynomials, and there's some like Gaussian envelope thingy. Very quickly, you're taught to think in terms of these ladder operators and numbers, so like excitation number. And then you say, oh, look, the eigenenergies are equally spaced. And if you define some operators that kind of move you between those eigenenergies, the Hamiltonian has this simple form. And the number operator has this nice property of commuting with the Hamiltonian. In some sense, it is the Hamiltonian up to scales. That picture is wonderful, but it doesn't represent reality in most cases for low energy harmonic degrees of freedom. You cannot buy off the shelf the equivalent of a single phonon detector the way that you can for optical photons. So in a world in which your more natural kind of quantities that you can access and measure are things like position and momentum, this is the way that you can equivalently write the Hamiltonian instead of quadrature phase space variables. And neither of these quantities commute with the Hamiltonian. And if you measure them, well, in some sense, this is a better representation of the state of the system, right? If you measure X and Y here, if you measure X, what do you measure? Well, quantum mechanics tells you that you will get a statistical distribution of probabilities, which essentially are found by integrating out the variable that you don't measure, y, in this two-dimensional function, and you'll get some Gaussian blob. We'd like to get away from this kind of picture into this kind of picture. And to do that, you require some kind of stronger nonlinearity, something which is not just harmonic oscillators linearly coupled to other harmonic oscillators. The electromechanical coupling that I described, that is nonlinear, but too weak. If you want to think about the interaction Hamiltonian, there is an electrostatic force between these plates. If you like, even if there's no energy stored in that LC circuit, there is still the electromagnetic vacuum fluctuations, the kind of single mode limit of the Casimir force, is going to provide a little force between these plates. And then the plates will have a 0-point motion. You can write out classically what that what that interaction energy looks like. It's kind of how the capacitance depends on position, the mean square voltage across the capacitor plates. You write that in a quantum language, and you get something which has some physical scales associated with the circuit and the mechanical object, and then the photon number operator times the mechanical displacement operator. That is not bilinear, right? That is a nonlinear interaction. And in principle, that gives you everything you would need to escape this kind of world of linearly coupled harmonic oscillators. But the problem is, again, that small parameter. The small parameter here of the 0-point motion divided by the separation of these plates, 10 to the minus 7, you're fighting a small parameter at like parts in 10 million range. And that means that this kind of effective interaction Hamiltonian is small. And when we pump it hard to turn on, to enhance that interaction, we also linearize it. So if you want to overcome that small vacuum electromechanical coupling, there's sort of two strategies. One is that you can arrange so that it's not just the 0-point motion of the voltage fluctuations across the capacitor that are, creating the interaction, but you could just, apply a DC voltage. You just get a static voltage that's present. Or you could slide between the capacitor plates a little thin sheet of material, which is piezoelectric. Basically, if I press on it, it develops an electrical polarization, basically from anisotropy in the material itself. Both work. Both give you a linear interaction that is now much stronger. And actually, both cases you get, in our experiment, something like 10 megahertz interaction scale, boosted by factors of 20,000 or so above our vacuum electromechanical coupling. But it seems like you have won a much bigger interaction, but now you really are going to have, again, a kind of linear interaction. It's going to be the coordinate associated with the voltage in the circuit that's linearly coupled to the coordinate of mechanical motion in either of these cases. Go ahead, Caden.
So it is linear, but there does seem to be something new here in that you have the A dagger, B dagger term, which was kind of off resonant before. Do you have to keep those or do those go away or?
Oh, depends on details, but in what I'm going to tell you about, you do need to keep them.
So even though it's linear, it is still a little bit different than before, right? Because before we didn't have those.
Yes, that's right. Although you could get exactly this arrangement in the previous case, the kind of linearized coupling, if you pumped on resonance, then there wouldn't be this kind of the upper sideband or the lower sideband is the thing that's resonant with the circuit. You'd be so, but that's if you at this point you can also say, look, it's nonlinear, or sorry, it's linear but strong. I could just make my electrical circuit nonlinear. I could add the nonlinearity through the electrical circuit, and I can do that by using instead of an inductor here a Josephson junction. A Josephson junction, look, it's a complicated, interesting phenomenologically complex object, but I'm going to treat it for the moment as just a kind of nonlinear inductor. And it's the basis of superconducting qubits. And then you can get a kind of effective interaction Hamiltonian, which is really like a two-level system that is coupled to the mechanical or displacement coordinate here. So in outline, I'll show you that it's possible to have a mechanical oscillator coupled to a kind of qubit, and it's going to form an interesting system. It's going to be a particle in a kind of quantum potential that's defined by the state of that qubit. It can act as an energy-sensitive detector of that mechanical oscillator, something that doesn't measure its position, but something that measures its energy. Strictly, it measures something a little different than energy, but it's definitely not just position. And I'll show you that we can use that to stabilize a highly non-classical state of motion. And there's a sense in which, if you think of superconducting qubits, sometimes they're referred to as being artificial atoms. I'll show you a sense in which you can think about the system as a kind of artificial molecule. So same basic setup. We're going to have an aluminum disk that's suspended above some metal electrodes, some aluminum electrodes. But now, rather than working with the fundamental mode, we're going to work with a higher order mode of that tightly stretched sheet of material. It's going to be this kind of, if you like, 2-1 mode. There'll be two antinodes of motion, and then a node right along the sort of symmetry plane in this picture.
So Konrad, you didn't, oh, I might have missed it. When you went to the superconducting circuit, can you go back for a sec? So you replaced it by sigma x, A plus A dagger by sigma x. So you're basically saying that you're among all the harmonic oscillator states that A and A dagger moves you around, you now can only have 0, 1.
That's right.
And that's because it's only parity that's distinguished by a superconducting circuit.
Actually, no. The Hamiltonian of the particular qubit we'll get to in a moment, but roughly, because the inductor is, this is not going to be a trans von qubit. It's going to be more old-fashioned than that. It's going to be a so-called Cooper pair box. It has a spectrum, an energy spectrum, which has many excited states, but they are profoundly not harmonic, as we'll see. They're very, very harmonic. And so we're just going to build our world around the lowest two states. That's, right. And when we do that, then we're sort of introducing like the Pauli operators as operators that take us within that manifold of just the two lowest lying states of the qubit.
But I just wanted to understand the physical degree of freedom that you're limiting to 0 and 1? Is it the number of Cooper pairs that are sitting on the island, or something else, some other degree of, it'd be nice to know what the degree of freedom.
It's so it is going to be charge in effect that we're coupled to, and Cooper pairs. We're going to work in a way where it is either a quantum superposition of like n Cooper pairs separated between two islands, or n+1 Cooper pairs.
Okay, perfect.
And those are going to be the low-lying states in this system.
Okay, thanks.
So our mechanical oscillator, again, vibrating aluminum. Oh, sorry, I should say that. In some version of this talk where I was going to tell you both stories, I would tell you both stories. But given the fact that we're almost an hour into this, I think I'm just going to tell you this story. And so this is about applying a static voltage. So what we're going to do is we'll have a 25 megahertz mechanical mode, and it's an anti-symmetric motion here, where these two anti-nodes of motion move out of phase, and there's a node in between them. And build a circuit where the electrodes that sit underneath that those two anti-nodes of motion, there are two of them, they're split, and they come out from under that drum, that sheet of suspended aluminum, and they're connected together through a pair of Josephson junctions. And then we can apply a static potential, a DC bias, to the upper drum head electrode. We can create a static potential that raises the potential of that piece of metal above some metals with neutral potential. And in particular, this upper and lower electrode, they are floating. They are not electrically connected to anything that you would call ground, but they have a capacitance to something that you would call kind of a neutral or ground potential. And so now what you get is a pair of electrodes. As you bias the upper drum here, the potential difference between these two electrodes, to the degree that this drum is not deflected at all, the potential difference is 0. That's just from the symmetry of the circuit. But as you deflect away from that, as the drum head vibrates in this 2-1 mode, you're going to preferentially lower this capacitance and raise this one, and vice versa. And that's going to create an oscillatory voltage across, well, it's going to create a voltage across these two terminals, where it is the coordinate of this motion that is directly creating that voltage. So we can make a kind of equivalent circuit for this, where we imagine there's a single Josephson junction shunted by some capacitance, sort of the capacitance between these two electrodes, and then a weak little capacitance that is kind of associated with some network of these capacitors. And then there's a voltage which does not appear explicitly in this picture. It is essentially how the potential difference across these electrodes depends on the coordinate x. There will be a linearly dependence on that. That makes the gate voltage in this circuit, that's this potential here, a kind of quantum variable. It's not a knob in the circuit. It's just a parameter we tune. It's a dynamical degree of freedom, which is the coordinate of this mechanical oscillator. We'll also add the knob, though. We'll also have an additional voltage that we can apply, which is designed to create a static potential difference between these two electrodes that we can control. So when you do that, well, you can ask, what are the energy levels? What are the excitations of this circuit? If you just pay attention to the capacitors, little capacitor, big capacitor, and we ignore this Josephson junction for the moment, we assume that it's essentially not present, it's an open. The electrostatic energy of the circuit is essentially are parabolic functions of the gate voltage. But it's a family of parabolas where each parabola is just labeled by how many additional Cooper pairs there might be on this little isolated island. And there's a special electrostatic potential where the electrostatic energy of that circuit is just as happy with one more as one less Cooper pair on the island. And that's this kind of crossing of parabolas here. If we now imagine that there's a Josephson junction coupling those two electrodes, that Josephson junction, in a kind of quantum language, what it is doing, it is annihilating a Cooper pair on the left and creating it on the right, and the Hermitian conjugate of that. And that lifts the degeneracy. To the degree that you make that Josephson energy pretty small, the rate at which the Cooper pairs are trying to tunnel kind of small compared to the electrostatic energy, then you can sort of just treat this in perturbation theory and you get a weakly split pair of states. And there's a parameter that controls where you live in this potential, and that's this gate voltage. One part of that is just this knob V0 that we control, and one part is this dynamical coordinate X of our mechanical oscillator. And so if you think about that, if we bias our static potential such that we live at this point in this energy diagram, there is now a qubit state-dependent force. I'm going to think of this two-level systems. I'm going to call it a qubit. Whether the mechanical oscillator now feels a force that either pushes it away from this kind of special place or pulls it towards, depends on whether or not the qubit is in its ground or excited state. That gives you a kind of qubit state-dependent force. If instead we were to bias right here, that force would vanish, but the mechanical oscillator basically, if I move it away from the special place, it's either repelled a little bit or attracted a little bit. That's acting like a kind of either repulsive or attractive potential that's trying to drive it to or away from this point. That's basically like a kind of additional spring constant. It's like a quantum spring, a spring whose spring constant is controlled by whether or not the qubit is in its ground state or excited state.
So, but in the second case, I would get pretty nervous about kind of Taylor expanding for the minimum state since it's going to fly away. So do you have some way of controlling that displacement to make sure it doesn't get too big?
Well, the point is, that there's both the kind of quantum spring constant and the one that's there just because it's an aluminum drumhead that's made of some material. And it is kind of stabilized by the fact. So what you're doing is taking a big positive spring constant and either adding a smaller positive number to it and making it a little stiffer, or a smaller negative number and making it a little softer.
Gotcha. So in this equation, you just wrote the K is bigger than the KQ.
That's it. That's right. And so in this world, you now have a kind of Hamiltonian that describes the system, where you have the Hamiltonian of the bare qubit, a Hamiltonian of the bare mechanical oscillator, and then this piece, which is a qubit state-dependent spring constant. Sigma z is 1. I've made my spring a little stiffer. If it's -1, I've made it a little softer. And you can really think about this in, I think, what is a kind of a chemist's picture, like a not a chemist. I think this might be like a Born approximation. If I have an atom and I think of the internuclear coordinate, sorry, molecule, and I think of the internuclear coordinate as being associated with slow fat nuclei moving around very slowly compared to the rapidly reconfiguring electrons. We can think of the qubit as a kind of the fast degree of freedom here that's defining the potential. And then the mechanical oscillator is the slow, heavy thing that's moving within that potential defined by the quantum state of the superconducting two-level system.
So Konrad, can you go back for a second?
Yeah.
So you mentioned this issue of, if you have a linear coupling between two oscillators, it's difficult to negotiate them to go into, Fock states. Is this issue fixed both off resonance and, well, I don't know how to say it, resonance, and it's fixed by both the top and the bottom?
Both this expression and this expression.
Both fix that issue because the qubit is not, because the nonlinearity of the qubit itself.
Essentially, yes. As it turns out, for reasons that have to do with the dirty effects of the Cooper pair box, this isn't going to be a very popular place for us to work. But this is, you can see what this is, right? This is a qubit state-dependent force or deflection of the mechanical oscillator. And that is something that is used in ion trap systems. You can get a kind of atomic state-dependent force on a trapped ion that's used extensively, like in trapped ion systems, to do quantum control of the mechanical motion of the ions. And that would, if our kind of our artificial atom here were cleaner, if it weren't basically the parameter here, V0, well, we control it. Unfortunately, the environment controls it in a noisy way. If that weren't the case, then this is essentially a very strong kind of, by the scale of things like this, force is quite large. It would displace the mechanical oscillator by many times at 0-point motion. But we're going to prefer this. We're going to prefer this regime, where it's really
right. But before you move on to the before you move on to the preferred regime, which I imagine, so now you're going to focus on the preferred regime, the lower one.
Yep.
I mean, can you just elaborate a little bit, like what does it mean from the less preferred one? Let's say you had control over V0. Like, how does that then accomplish your task of better than the linear one, where you want to put a system into the Fock state of B, I guess, the oscillator Fock state?
Sorry, are you asking me the question, if I want to put my mechanical oscillator into a Fock state, would I, without dirt reasons, prefer this or this?
No, I'm asking more like, even at a schematic level, suppose you had full control of the first of the top Hamiltonian, which seems simpler. What would you do that you couldn't do before, without the Cooper pair box, that allows you to put it into the Fock state, which you couldn't do before?
Sure.
If you like, what's the protocol? Like, what would you do?
Good question. Let's see if I can answer that one on the fly. I'm going to try not to rely on a lame statement. And so if Leo,
Sorry.
No, it's a good question. I think in this case, what I could imagine doing is like a polaron transform, where what I would conclude is the the static location of the mechanical oscillator depends on the state of my qubit. And I think that's actually alone is going to make my qubit, it's going to make my mechanical oscillator anharmonic.
I see. Right.
Then in some sense, my mechanical oscillator has become a qubit. It would absorb energy at a frequency which would be to go from 0 to 1, which would be spectrally separated than to go from 1 to 2.
Oh, I see. Okay, so I'm just trying to, so I'm trying to understand the essence of like, what features does this Hamiltonian have to have in order to be able to put it into the Fock state? You're saying it's this breakiness of this linearity or equal spacing of the oscillator states.
Yes, that's right. But in a sense, the Fock state is sort of like an awkward one to think about. But you can understand that I should also just be able to put this system into a quantum superposition of two coherent states pretty simply, because if I prepare the qubit in a superposition of ground and excited state, then the mechanical oscillator is going to evolve as if it were simultaneously, it had one force and another force. And if I let that evolve for the right amount of time, so those look like they would end up in well-separated places, and then I would deterministically put the qubit back into the ground state or something, I would have created a Schrodinger cat state.
I see. Okay, thank you.
So this Hamiltonian, it's kind of a familiar Hamiltonian in a world of circuit quantum electrodynamics, which is now a big deal. So at charge degeneracy, what we can say is, look, let's just write this as the bare qubit and mechanical oscillator Hamiltonians plus this interaction term. Now, our two systems, the qubit and the mechanical oscillator, they're at wildly different frequencies. One is going to end up at a few gigahertz, about 4 gigahertz. That will be the superconducting qubit, and then the mechanical oscillator is down at 25 megahertz. We would be in a far dispersive regime of this Hamiltonian, and you can work in a small parameter, which is essentially this coupling rate divided by the detuning. And when you do that, you get a dispersive Hamiltonian, which is basically a qubit state-dependent resonance frequency of the mechanical oscillator, or a phonon number dependent frequency of the qubit, where the frequency scale that controls that is this so-called dispersive shift. It's a little different than the usual superconducting qubit and in the cavity story of the dispersive limit of the Rabi Hamiltonian, basically because the mechanical oscillator is so low frequency that compared to the qubit, that the sum and difference terms are both of the same order of magnitude. Usually in this world, this term ends up being a lot smaller than that term, and it ends up in the denominator of some expansion, and you drop this thing in a rotating wave approximation. Actually, both terms contribute here. And in the other consequences that here we'll also want to hang on to or think about these terms that also appear. These are kind of terms that appear to that are, you can see B dagger squared or B squared terms. They are terms that in some sense annihilate or create phonons in pairs. And that's the kind of dispersive limit of this Rabi Hamiltonian. The bare scale here, G naught, sort of how strongly coupled our mechanics is to our qubit, that's 22 megahertz. The dispersive shift in this far dispersive limit, that's going to be much smaller, about 260 kilohertz. You can think of this as a kind of, like, if you think of it from the qubit's perspective, this is a kind of Stark shift that shifts the frequency of the qubit proportional to the number of phonons in the mechanical oscillator. And that's going to get at the thing, Leo, about how might you measure the number of phonons. And then there's a term like this that will put sort of sidebands onto the qubit spectrum. Will it be possible to excite the qubit or de-excite the qubit by annihilating pairs of phonons or creating pairs of phonons? So what we can do in that system is, now what I'll plot is the difference between the qubit ground and excited state as a function of this control parameter. And now this point at degeneracy, where we just have the qubit state-dependent spring constant, that's a sort of 4 gigahertz frequency. We'll park at that point. And what we want to do is understand how the qubit is going to, how the mechanical oscillator is going to modify our qubit spectrum. And to get an experimental handle on that question, what we'll do is turn off the big DC voltage, so turn off the coupling of the mechanics to the qubit, but apply an AC voltage at the mechanical oscillator's resonance frequency to the qubit, and then look at the qubit spectrum. And you can see here, this is an expression of the qubit frequency as a function of this control parameter. And now we're just saying, well, I'm going to make this a kind of classical parameter that's a function of time. This is this kind of hyperbolic curve here. I can expand that both in terms that is sort of the coefficient of this oscillatory gate potential, and then the kind of frequency dependence of that. And so you can see that the qubit frequency, it's become time dependent in a way that you can understand this thing is just going to be a static shift that depends on this amplitude, and then there are going to be some sidebands created by that oscillatory function. This is a completely classical modulation of the qubit spectrum, which we're going to use to understand what our mechanical oscillator is going to do. So when we do that, we can plot the qubit spectrum. This is the probability that we excite the qubit in the color axis. The strength of the AC drive expressed as if it were the Stark shift applied by the mechanical oscillator in units of frequency, and then the spectroscopic probe frequency of the qubit. And what we can see is as we turn up, essentially it's lambda squared growing on this axis. As we turn that up, we can see both the Stark shift and the appearance of all of these 2 omega sidebands. What in fact we can do is say, look, if I were to measure the qubit spectrum with a mechanical oscillator prepared in a Fock state, it should have a spectrum that essentially looks like a vertical line cut in this picture. And so if I'm in a statistical mixture of such number states, I could deconvolve that line cut. That's in fact what we do. So if we imagine this would be the spectrum of the qubit if we could prepare the mechanical oscillator with no phonons. If we could prepare it with one, the shift is regrettably not that big compared to the kind of spectroscopic line width of the qubit. But if you make it somewhat bigger, like 15 phonons, that gives you quite a big shift, and you can sort of see the sidebands appearing here as well. 30. And if you ask, well, if I had a statistical mixture, say a thermal state associated with a 25 megahertz mechanical oscillator, cooled to a few tens of quanta inside of a dilution refrigerator, you'd get a curve that looked like that. That's in fact what we see. We measure the qubit spectrum when we have the mechanical oscillator coupled to it. We can do a kind of deconvolution procedure and express the probability that there's a certain number of phonons in the mechanical oscillator as a function of n, essentially finding its phonon number distribution through that deconvolution procedure. And then if you like, you can say, what would I expect for a thermal state with 20 phonons, which is about the right number for 25 megahertz mechanical oscillator and a 20 millikelvin dilution refrigerator.
So is that the thermal fit, just assuming it's a harmonic oscillator, or you're including the coupling to the?
It's actually just assuming that it's a harmonic oscillator, and it is still a pretty good harmonic oscillator, as it turns out. And you can shape your mechanical oscillator and give it a coherent amplitude on top of the thermal amplitude, and you can extract both the coherent amplitude and the thermal contribution. You see a very different qubit spectrum. Nevertheless, you can extract these phonon number distributions. So we have a meter that measures something like the energy of the mechanical oscillator. When we measure the qubit spectrum, we're getting at the phonon number. We're getting a kind of phonon number distribution. And our resolution is maybe not quite good enough to prepare in a single Fock state. It's a few, about 7. Maybe you can sort of see that here. The qubit, the Stark shift associated with one phonon is about 1/7 of the line width of the qubit, the kind of intrinsic line width of the qubit. And that's actually going to spoil the ambition to really get at one phonon with this device. But you can still soldier on in that situation. So you can control the number of phonons using dynamical processes of the qubit. In particular, you can drive the qubit from its ground to the excited state in a way that preserves phonon number in some kind of energy level diagram picture where phonon number is increasing as we go to the right, and qubit energy is, or in fact, system energy is plotted vertically. You could drive, it turns out to be a 2-photon transition, in such a way that you would drive the qubit from its ground to the excited state, but extract one phonon from the mechanical oscillator. And that would occur at a slightly different frequency than this direct transition. And likewise, you could excite the qubit and create one more phonon in the mechanical oscillator. Again, even a different frequency than this transition. So you can spectroscopically address these different transitions. And so what we can do is imagine that we start in a thermal state, and for each number in the mechanical oscillator, the qubit would have a slightly different frequency. We can tune our qubit drive to be resonant with the population of the mechanical oscillator, say here, but that would be a transition that would drive the mechanical oscillator to have one more phonon in it. Again, and we can do that with a resolution of about 1/7 of the resolution we would need to pick out a single such transition. So there are a few of these being driven simultaneously. That's why this is a kind of fuzzy blob. And what we'd expect is if we could do that, we would take the population out of the mechanical oscillator that was spectroscopically addressed by this drive, and move it up to higher energy. And then if we did that, we could then measure this distribution using our little energy meter. And that's in fact what we do. So this is a qubit spectrum in thermal equilibrium in orange. And when we drive the very lowest part of the energy part of the distribution, the very lowest phonon number part of the distribution, and try to push it up in energy, and then measure spectroscopically after we've done that. And here, these are the extracted phonon number distributions from our deconvolution procedure. As we address a kind of higher part of the population, you can see you leave some of the lower numbers behind, nevertheless still pushing things to higher number. You can dig a little hole in the phonon number distribution and sort of push it around. And that's sort of the evolution as you go up and up in the phonon number that you address. You can take just this little tail in the high number part of the distribution and push it up, leaving the low number unaffected. You can, of course, do the reverse process. You could spectroscopically address a particular section of the phonon number distribution and drive it to lower energy. And dig little holes and push things to lower phonon number, push the phonon number. So this is the thermal distribution. This is the qubit spectrum in a thermal state. This is the extracted thermal distribution, just as you'd expect for thermal distribution in our deconvolution procedure. Now we're going to try to cool by sort of taking the 8 phonon number part of the distribution and pushing it lower in energy. And sure enough, we can dig away the sort of 8-ish region of the distribution and push it lower. It's a non-thermal distribution, but in a loose sense, I'll think of that as colder. And you can get it quite cold in the sense that you can take this object, which usually had only a few % chance of being in the ground state, and push it up to essentially 50% chance. So this is like cooling through a 2-level system.
How well can you populate a single end state?
We don't
Not
have
necessarily 0, but maybe, I don't know, kind of drive, n+1 and n-1 and kind of converge.
Oh,
at
thank
some
you
point.
for, you're doing a great job of anticipating my next few slides.
I'll be patient.
Other questions though, before I do that?
I had a question.
We'll just
about
alert you to the time, Konrad, that we should wrap up in the next few minutes here. We started a little late, so take a little bit extra, and there are lots of great questions, but we don't want to go too late. Very
good. I'm close to the end here. I'm going to kind of, I'll do what Yakov has proposed. What we can do is start with the blue sideband, the thing that pushes me higher in energy, spectroscopically addressing only the low frequency, only the lowest part of the population, and then chirp it, push it up in frequency. Really just kind of like snow plowing the phonon number distribution higher. And that's what we'd expect to have happen. That's our simulation. That's the data showing here the phonon number distribution being kind of chirped and pushed in a sort of driven dissipative way up to be a non-thermal distribution, but one which is higher energy. And just as Yakov proposed, we can also now have like a little wall where we turn on the red sideband that cools or pushes the phonon number distribution down in energy and smash the population, trap it between those 2 drives as we chirp one into the other. So again, that's our expectation for phonon number distribution probability as we chirp the blue towards the red, compressing the distribution. Again, a completely kind of driven dissipative process. That's the data. And so we can smash the phonon number distribution between these 2 sort of somewhat fuzzy walls. What we can't do is quite get down to a single phonon number that way, but we can get to a distribution whose width is much narrower than the width of a coherent state of that average energy. So what we'll do is do our very best job of trying to squeeze the phonon number distribution in energy and then measure its energy distribution. So this is the qubit spectrum. After we do that, the deconvolution procedure gives us a distribution where the width is, the variance, I should say, is a quarter of what it would have been for a coherent state if we were in a vacuum of mechanical motion displaced from the origin in phase space, essentially one of these low entropy but ultimately classical seeming states.
So should I think about the squeezing of the number is what's giving rise to the nice oscillations in the qubit? Is that why?
No,
Not so simple. Yeah,
that is actually something different,
Okay.
and that's important. It's about those kind of non-phonon number preserving terms in the Hamiltonian. They end up mattering a lot here, and we'll do that quickly here just to wrap up. So we didn't quite make it in this kind of concept to a single phonon, but what we are able to do is prepare profoundly non-classical distributions of phonon number, things which are energy squeezed below this kind of coherent state or Bosonian limit. In order to just tell you about these sidebands, that's if I were in a coherent state, that would be the number distribution, and that's the associated qubit spectrum that we should have measured. To tell you about these little sidebands that have appeared, that's about the kind of vibronic transitions in this artificial molecule. All right, Anand, I'll let you ask your question, but please understand that I'm going to rush a little bit.
Maybe I can just ask towards the end then.
Okay. I'll get this wrapped up. So I'm going to write down our Hamiltonian again with our qubit state dependent spring constant, and then plot the energy for the qubit in the ground state and in the excited state, where I'm just sort of shifting the two potentials so that they overlap at zero. And understand that what's happening is that when the qubit makes a transition, the shape of the potential is changing. And in a kind of like chemical physics picture, the potential is changing on a time scale of the qubit transition, kind of gigahertz frequencies, very fast compared to the mechanical oscillator's resonance frequency. It's as if we're making a kind of sudden perturbation to the mechanical oscillator's Hamiltonian. We're kind of suddenly changing its spring constant and asking questions like, how well does that particular phonon number state in the ground state manifold overlap with the excited state manifold? And the answer is not perfectly. And that's the origin of these little sidebands that we see. They correspond to essentially probabilities that after the qubit makes a transition, we are no longer in the n state of the mechanical oscillator, but in the n plus or minus 2 state. And so you can draw that, you can draw the kind of wave functions for these potentials, both in the ground state and the excited state, and they don't overlap with the same n perfectly, nor do they like have zero overlap with the things sort of 2n away. And that's what we're seeing here. We're seeing these vibronic transitions. Furthermore, because it's hard to really stabilize the qubit so it doesn't drift away from this special place where the first order terms vanish, we can also see not just the kind of vibronic transitions associated with changing the spring constant, but also changing the kind of 0 point position of the oscillator. That's sort of the static force. And both of them are present. This is really resolving the mechanical recoil associated with the qubit transition. It's really Frank Condon physics in some kind of like artificial molecule. All right, I think I better just more or less wrap up there. I'm going to make that the last slide here.
Great. Thank you, Konrad, for the great talk. Anant, you had a question, and then Saeed.
Yeah, I wanted to ask about the thing that looked like cooling. So it kind of resembled resolved sideband cooling in atoms. But in atoms, we have like a spontaneous emission that like gets us down from E to G without changing N. So is there some equivalent step here which changes the qubit level without changing the harmonic constant?
So you're sort of asking the right question and hitting where it hurts. The qubit will spontaneously decay because it's a material thing which has dirty internal degrees of freedom that absorb energy, and those things absorb energy, and so the qubit spontaneously transitions from excited state to ground state at a rate of kind of characteristic timescale of a microsecond or so. If this vibronic physics that we see, of course, it would spoil the fact that you wouldn't change n. Fortunately, that's only really turning on when n is relatively large. Like from n to go from 2 or 1 to 0 does not have much probability of, when the qubit is relaxing, it doesn't have much probability of actually exciting the mechanical oscillator. When n gets up to 40 and 50, and I think this is the same thing that's seen in trapped ions, for example, then you're sort of outside of this Lamb-Dickey regime, and you start to see exactly that sort of sideband physics that makes it more difficult to cool. Did that answer your question?
Yeah, I see. So in that case, if it's reasonably cold to begin with, you can actually get it colder because you're in the Lamb-Dickey regime.
Yeah, that's right. That's a fair way to say it.
I see. Awesome.
Saeed?
Yeah.
Yes. So my question is that now, if I want to couple the whole thing, the electromechanic or optomechanic, to the matter, to study properties of the matter, is it possible? Is it even strong enough, the coupling between these two? Is it possible to, let's say I'm trying to study a superconductor, which is coupled to this electromechanical system, and study the properties of superconductor using the back action on the mechanical modes?
Imagine it like I would have some other material or some other object that would be coupled to the mechanical mode, and now maybe am I trying to cool the matter or something like this using the mechanical oscillator or something like this? Like maybe it's got some internal degrees of freedom that can give up energy to the particular mechanical mode, and I can extract that entropy in this way.
Mm-hmm.
It's an interesting idea. For real materials degrees of freedom, I don't think we've ever imagined that we could do that at a rate which would be fast enough to be relevant. The thing which we have thought about loosely, in a shallow sense, is if you have nuclear degrees of freedom, things with very long relaxation times, that maybe you could get into a regime where you could cool the nuclei through the kind of mechanical motion, and the mechanical motion you would cool using these electromechanical effects. You can imagine that such a thing is possible. Like that's sort of a thing where it doesn't seem outrageous that's possible.
I mean, mainly I'm asking because I know that the people do this cavity stuff with the superconductors, right? They try to study and they put the superconductor into the cavity. Now, if the cavity, you have a cavity which also has a mechanical coupling to it, will be interesting to see if it has any particular effect on the.
Well, for like I'm imagining when you said a superconductor, I thought what you had in mind was some exotic piece of condensed matter physics which needed to get colder than your dilution refrigerator would get. But it sounds like this is more like having a circuit QED system, like a cavity or an LC circuit coupled to a qubit, coupled to a mechanical oscillator?
No, I'm really thinking about the putting the cuprate, a cuprate superconductor.
Oh, cuprate superconductor.
Yeah, inside the electromechanical or opto-mechanic system, and try to see if it has any effect on the mechanical side.
I think that the most honest answer is I've never thought about exactly what you're proposing. My kind of seat of the pants guess might be that the timescales on which things relax in a cuprate superconductor might be way too fast for the rate at which we can extract entropy using a single kind of relatively high Q mechanical mode.
I see. Yeah, thank you.
Great. Other questions?
Conrad, I had a quick question. Well, I don't know if it's quick, but I have a question. So, let's set aside the thermal issues, the mixed states, and just focus on, you have perfect cooling and you've cooled down to a quantum, single state, quantum mechanical state. How do you, let's say you're in some superposition of n states, the number states, you're in coherent state, let's say. What would your, I would imagine your signal would look, again, this distribution of qubit being, what was it, a transmission you were, or I forgot what you were actually measuring.
Yeah, I'd never talked about it. The qubit is actually coupled to an LC circuit, and we use the LC circuit to learn about the state of the qubit, and the state of the qubit to learn about the state of the mechanical oscillator.
Good. So, but it's some transmission, qubit dependent transmission.
That's
qubit state dependent transmission. So, if you were in a pure state, but it was a coherent state, you would also not see peaks, I would imagine, or would you? I feel like the essence is not, you kind of presupposing by using a language of number states, you kind of presupposing like, and focusing on cooling into those states, you presupposing or excluding the more subtle thing where there's a, single state, but it's a superposition of number states, and then, distinguishing that from, let's say, the thermal.
Well, let me sharpen your question specifically. Like,
yes, please.
Konrad, how would you tell the difference? Let's say you could show that you had a 50-50 possibility of having one phonon and two phonons.
Right.
How would you show me that you could see any coherence between those two? Like, is that a statistical mixture or is it a pure state?
Or what would the signal look like in that case? In the case of, let's say, coherent state, what would your transmission signal look like?
So you're asking a good question. The answer in our current experiment, like in this sort of generation of experiments, would be that the time scale over which we would average in order to establish that there was one or two would be much longer than the relevant coherence time of the mechanics. And in fact, we would not be able to distinguish the statistical mixture of one and two from coherence, because essentially, now, if you would say, okay, look, if our qubit coherence was good enough, then you can imagine that what we would do is a kind of measurement of phonon number distribution after a coherent displacement of the mechanical oscillator, or in fact, if we were good enough, we could do parity to decide whether the the system had an odd number, even number of phonons, and that would simply be because the dispersive shift would be some time, and it would be approximately proportional to the phonon number, and we would let the qubit evolve in a superposition of ground and excited state until such a time that the even states would end up on one side of the block sphere, the odd states on the other, and then rotate the qubit, and then measure whether it's in ground excited state. And you might know that the expectation value of the parity, that the one way to understand what the Wigner function is it's the expectation value of the parity of a harmonic oscillator distribution after displacement by alpha. So if I displace a point alpha in phase space, it's actually by minus alpha. If I'm going to point alpha in phase space, if I measure the average parity at that point, that would be, or sure, what is it? If I measure the Wigner function at that point, that would be the parity that I would measure if I took my harmonic oscillator state, displaced it by minus alpha, and then measured the parity. And so that's how you would get at, any kind of Schrodinger cat-like state, phonon number, some Fock state, any superposition of Fock states. That gives you, in some sense, the complete map of the Wigner distribution, and it would require levels of coherence of the qubit, about 3 orders of magnitude better than we are right now. So the second half of the talk, which I'll give in some other year, that's the process of using piezoelectricity rather than this kind of DC voltage concept.
I see. Okay, well, thank you. Yeah. Are there other questions? If not, then let's thank Konrad again and break until 2 p.m. Boulder time for Ian Spillman's lecture. Thank you, Konrad.